Okay, in this part, we'll finish up with our example of the heat pump model, and we'll look at the data. We'll look at entering the data briefly and develop sort of computing the coefficients and examining them in GLHEPRO. Okay, so here's GLHEPRO, and if we go to the select heat pump, we can choose heat pumps, and if you look here, you'll see that we have a variety of heat pumps. For each one, we've chosen, typically for watered air heat pumps, we've chosen a specific source side flow rate and a specific air side flow rate also. So that's why you see so many GPM, so many CFM. Unfortunately, it's just, it's impossible to have every combination, or at least for me, or at least with the software as it is now, which just treats every combination, or every combination of flow rates. That would have to be a different heat pump model in the library. If we had a more sophisticated library, we might be able to choose a heat pump model, and then maybe we could separately specify the flow rates. But it's not really clear, for example, that we could, for all manufacturers, automatically compute corrections and so on. So I think in many cases, the user is going to end up entering their own heat pump. I'll also say it's more or less, at least the way we run the GLHEPRO operation, impossible to keep this up to date. So with new models. Okay, so I think what we'll do, let's look at adding a model, and we'll just say add a heat pump, and you see I have some sort of invented model categories, and I'm going to invent a new one, or I'm going to try to. So we'll just call this, give it my initials, JDS, and call the first one 3-ton uncorrected. I think what we'll do is we'll create a model for the uncorrected data, and then we'll create a model for the corrected data, and then we can actually check on us, for one example, just check to see the difference in size. Okay, so we have to choose whether we want a linear or quadratic fit. We enter the cooling loads, and you can see this is going to be a bit tedious, so we'll enter a couple, and then I'll pause it and enter the rest. So if you go back in the notes, well, I guess we're kind of stuck here. So this was 30, 33.7. Heat of rejection in kBTUs per hour, that was 38.2. And the power input in kilowatts was 1.32. Okay, so we'll pause there rather than having you watch all these things get entered. Okay, so all those values are entered, and we can hit OK. And let's go ahead and enter the heating loads. And by the way, there is an option to paste these from a spreadsheet, which is actually what I did while I was supposedly entering them by hand. My spreadsheet that I originally developed had things in the wrong order, so I had to reorder them, and looks like I made some kind of mistake here, so this should be the heating capacity and the heat extraction rate and the kilowatts. And if we converted the kilowatts to BTUs per hour and we added to the heat extraction rate, then we would get the heating capacity. So it will take this up to 10 values. I copied it, and now I'll paste that. It's okay. And by the way, on these cooling loads, it would only take 10 values. We actually had 11. So I just chopped off the 120 Fahrenheit row and did that. Okay, so now we've got a complete set of data. And what you can do, you can view the coefficients. So this is the heat of rejection divided by the cooling provided versus the temperature. And you'll see here, obviously, this straight line is not a very good fit. Right? So that would be one reason to go to a quadratic fit. Now we'll see it works, fits pretty well. Right, at least over the range of operation. You can see it starts to turn back up here, which is sort of non-physical, but that's a necessary consequence of using a quadratic equation. At some point, it will start to turn up, and of course, it will go to infinity here and so on. It's only meant to be operated within the range of the data. Let's see. Let's look at this curve for the power versus temperature. There it is. So we can, at least we can predict pretty well what the power will be. Okay, and then heat of absorption versus temperature. Right. It's just a little bit of this data. Sometimes the data are a little bit rough, but yeah, it still fits pretty well. And power versus here. So this is one of the points of the tool, is you can examine and see how well the fits work. Okay, so that's really all we need. And if we've selected that heat pump, and we can go ahead and this is just the file I was working on with some students, but we can go ahead and use it. We'll size this, right? Okay, and it's 70 boreholes, 630.5 feet deep, which is a bit, probably a bit deep for around here. So we probably need to go to something larger. Let's go ahead and do that. And oops, if we say build our own, 10 by 16, or let's try a 10 by 14. Now that may have a slight difference on the flow, so I'm going to recalculate, or that will have a difference on the flow per borehole, so I recalculate the borehole resistance. Let's just size this again. Okay, so 319 feet. So that should be at least a reasonable choice. Okay, let's make another one. Let's make the uncorrected heat pump. So we're going to add a heat pump. It's going to be a JDS model. And it's going to be a 3-ton corrected. Only now I'm going to go right over to the spreadsheet where I've already got the data, and I'll get that. Okay, so I've got the spreadsheet open. Now we've got our 4 columns, 3 columns of data, the total cooling, heat rejection, and the kilowatts. If I copy that and then come up, pass over to GLHEPRO and just paste that in, we've got all the data in for that. And for heating, we're going to take the same approach. Okay, we can check the curves. Again, a linear curve probably isn't good, so go to quadratic. Yes, fits pretty well. Just check this. Yes, and it fits reasonably well in this range also. All right, and of course we expect for heating, our temperatures are generally going to be more in this range, and for cooling, or maybe in this particular situation it's a bit warmer. And for cooling, right, we may be somewhat higher. So if we select that, and now we can run this. We've not changed anything else in terms of the number of boreholes or anything. And if we size, we get 327. So we had 319 before, right? So this is, what, 9 out of 300 sums, so about 2 or 3% difference in size. Okay, that's the example for modeling a heat pump in GLHEPRO and adding it to the library. And I don't think there's much else to say about it here. You can go back later and check the data that were actually entered, and you could change them if you want and so on. But in any case, that's the example. So we'll stop there.